Copyright in these lectures is either owned by the ANU or a third party who has licensed the ANU to use it. Students may use the recording for personal study only. No lecture may be communicated online, copied or shared without the prior permission of the ANU.
Okay, let us set sail. So, talking about time series, what I'm going to do, by the way, when we finish sort of working through all of the different methods, is I'm going to try and then summarise a general procedure for dealing with time series, and that will help you get going on the second assignment, okay? So, we've done trend, in other words, where is the series going, ignoring the wiggly parts, and assuming that the errors are zero mean. I'm just going to turn this mic down a little bit because it's echoing a lot. Let's see if this works. Is that better? Same? All right. Okay, nothing happens. All right. So, trend, and in the case of the alcohol data, the trend was sort of this up, down, up, so a cubic trend was what we ended up fitting. Low S kind of told us the same kind of thing. Then we've got quarterly data, so the data is measured 4 times a year, and we kind of know that, you know, for this particular setting it makes sense that alcohol sales are going to be high in summer and low in winter, so we're going to fit different constants for each of the 4 seasons. That's going to modify our series in a systematic way. Now, one thing that needs to be true about the seasonal effect is it needs to be regular, okay? Someone asked me a very good question yesterday, because the original series had that look of wiggliness. So let's have a look at that original series. I'll just go back and do that. We'll start from there. So that's just what you get if you just plot the series itself, so it doesn't want to look like that. Let's do it again. Take the whole screen, there we go. So you see that sort of up, down, up thing, and then you've got the wiggly part, okay? So we went ahead and we fit a trend seasonal model, so a cubic trend plus a constant seasonal, and then we got the residuals from that, and we plotted the residuals, so that plot looks like that. No, sorry, where is it? Let me find it. Sorry. This one. Okay, so this is the residual series. And the question that was asked yesterday was, well, hang on, we had these regular periodic bits, right? And they don't seem to be gone, right? This thing still goes up and down in a way that you might think of as some sort of systematic periodic behaviour. But periodic means every spring it does something, and it does that same thing. Every summer it does that same thing. So when I count the dots between the peaks, I'm always going to get 4, right? Between the peaks it's going to go summer, autumn, winter, spring. Then I start another cycle. It's regular. Right? Exactly 4. Not 3 sometimes, not 5 sometimes, 4. Always, okay? Now look at this. Yes, it has peaks and troughs. But if you count the dots between the peaks, it changes from one peak to the next. That's not regular. Regular means it happens every 4th one, okay? So you're only going to fit seasonal behaviour if you see regular repeats. Irregular repeats go into noise, okay? Irregular repeats go into noise because they're not really repeats, right? You can't predict when the next one's going to happen. With the regular stuff, you can absolutely predict what's going to happen. In summer, it's going to be high, and you know that, right? So regular is the key there. So we went ahead and we fit that trend seasonal stuff, and this is the irregular part, or the noise part. But as we talked about yesterday, this is not white noise. White noise means there's no dependence From one point to the next, you've got independent, brand new information. These are not independent. They're correlated with one another. They are autocorrelated. If I know what the value is now, I've got a better shot at predicting what it'll be tomorrow than if they were independent. Okay? Because it's a noise process, my best prediction is that the next value will be 0, because you always predict the noise to be 0, but if it's on the way up, you kind of have a hint that it's going to keep going up. Okay? Your best prediction is still 0, but you can kind of expect it to build up, and then when it starts to come down, it'll keep going down. So we were going to fit different models to this to try to understand the nature of this dependence. So we talked yesterday about a very simple model called an AR1 or a Markov model. So here it comes. Oh, that's a little big. Let me make it a little smaller, if I can work out how. There we go. So we fit a Markov model, which is an AR1. So there's the formula for the model there. X now is equal to some constant, which is generally smaller than 1, times x one time period in the past plus error. So what this model means is there is explicit dependence between x now and x one time period ago. So in this case, x last quarter. Now, if x now is related to x one time period ago, and x one time period ago must therefore be related to x two time periods ago, it is clearly the case that x now must be related to x two time periods ago. But that's implicit dependence. This is what's called short-range dependence. xt depends explicitly on xt minus 1, and then through that, implicitly on xt minus 2, but not explicitly. Okay? There is no model relationship between xt and xt minus 2. This is cascading dependence. All right? Now, there are longer range forms of dependence, so we could fit what's called an ARP, an autoregressive of order P model, where we explicitly say x now depends on x one time period in the past, x two time periods in the past, right up to xp time periods in the past. So explicitly depending on values going back into the past. Okay? The question for us is, well, what should P be? And that's what we're going to try and answer. Yeah. We should have an error term. Well done. Plus epsilon t. Absolutely. The error term disappears when we fit it. It's there until we fit it. Excellent. Because when the assignment's marked, if you put the error term in before you fit it, I'm happy. If you put it in after you fit it, I'm sad. So it's a message I want you to get. Awesome. Okay. Big question is, what is P? How do we work out what P is? How dependent is the series that we've got? And that's a question we've got to address. Okay? So we're going to talk about two tools that are going to help us determine what P is for any given data set. Okay? Those tools are called the autocorrelation function and the partial autocorrelation function. So what are these two things? Well, there's formulas for them in the notes. Let me just tell you in real words. What's the ACF? It measures the correlation between xt and xt minus k for k equals 1, well 0, 1, 2, 3, and so on. Now, correlation when k is 0 is the correlation of xt with itself. What's that? 1, right? So the first one's always 1. This is the 0th one. And then it measures, on average, what's the correlation between xt and its immediate past, xt minus 1. Okay, you get a number. Then it does that for xt minus 2, xt minus 3, and so on. So that's what the ACF measures. Now, if your series is well behaved, if it's stationary, then these correlations have to slowly go away, right? So this is like memory. This is like memory. For an independent series, x has no memory, right? If I give you x now, and I say to you, predict x tomorrow, x can't do it. Tomorrow, x can't tell me what it was yesterday. New information, independent, okay? So an independent series has no memory. xt doesn't care what x was yesterday, it just doesn't, because it's doing its own thing, completely independent. In a correlated series, in an autocorrelated series, x does get information from the previous day. So if it's really short-range dependence, then you should see a moderate correlation between x now and x1 time period in the past. But then, if you go back 2, 3, 4 time periods, that should disappear fairly quickly. It's got short memory, okay? A bit like me. I remember what happened yesterday, I can't remember last week, right? Yeah? So, we want these autocorrelations to die down. So, if xt as a series is stationary, then the ACF should damp down, okay? It should damp down. So I'll show you a picture in a second, see what I mean. ACF should damp down. Okay? So what we use the ACF for, the autocorrelation function for, is to determine whether our series is stationary. Okay? That's its use. So you look at the ACF. If the ACF seems to be damping down, I'll show you a picture, seems to be damping down, then your series is probably stationary. So here's the ACF. There's a command in R that does both of them. The command is called ident, capital I-D-E-N-T, stands for identification. The top function is the autocorrelation function. So what am I plotting here? Okay, this first, I'm going to call these things spikes. The first spike is at 0, lag 0, which means xt with xt. So that should go to 1. Right? The correlation between anything and itself is 1. The next spike, this represents the correlation between xt and xt minus 1. Right? Just one lag. This is the correlation between xt and xt minus 2, 3, 4, 5, 6, 7, 8, 9. You get it, right? Goes all the way out to 20. See those dotted lines? Those are large sample bounds, significance bounds. So, if those spikes come down and then go within those two dotted lines and stay there between the two dotted lines, then your series is stationary. So that's what you're looking for. So you plot the ACF, you look for those spikes, those vertical lines, to get smaller in size. They can go negative, that's cool. We're looking at their size. And then they've got to stay within those dotted line bounds. Okay? And if they do, your series is stationary and you're happy. Okay? So that's the ACF. What's the PACF? All right. Let's go to a new sheet of plastic. All right. What's the PACF? P-A-C-F. And let's make it go down there. So P stands for partial. Okay. All right, how do you get it? First of all, you fit an AR1. So that is xt is A xt minus 1 plus error. And then A1 xt minus, what is A1? Okay, that's the question you ask. What is A1? Then, fit an AR2. That's xt is A1 xt minus 1 plus A2 xt minus 2 plus error. And from that, pull out A2. Okay? And so on. Keep on doing this. Fit an ARP, which is xt is A1 xt minus 1, all the way up to AP xt minus p plus error, and pull out AP. Okay? So those are the steps. Fit an AR1, pull out A1. Fit an AR2, pull out A2. Fit an AR3, pull out A... That's where you say 3. All right, now you know the rules. Fit an AR4, pull out an A4. Thank you. Fit an AR5, pull out an A5, 6, 7, P, right? And you get to P. So what we're doing is we're pulling out the last term in each of an AR 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, P. Okay? Now, if that last term is significant, you should fit that model, right? So if A2 is significant in an AR2, then an AR2 fits. Okay? If the last coefficient in an AR2 is significant, then an AR2 fits. If that A2 wasn't significant, what would you do? You'd slip back to an AR1, right? Okay, so that's what we're doing. So now, let's go back over here. Go back to the picture. So, here it comes, there it is. Okay. This is an A1 from an AR1. See how it's up here and it's outside the dotted lines? So that one's significant, all right? Then, this is the A2 from an AR2. It's inside the dotted lines. It's not significant. There's the A3 from an AR3. See, it's still inside these dotted lines. Not significant. Not significant, not significant, not significant. You go all the way along. None of them poke their heads out. Okay? So here's how you use the ARP, the PACF, the partial autocorrelation function. You start here and you run along until you find the last one that's poking outside the dotted lines. Okay? So in this case, the last one is the first one. Right? The last one that pokes outside the dotted lines is the first one. That says choose an AR1. Okay? Now, let's play a game. Let's pretend this one came outside the dotted lines. Let's pretend it was the pen. Went down to here. Okay? Then what you do is you run along and you go outside, inside, outside, inside, 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 inside. They're all inside the dotted lines. If this one was outside, that's the last one outside, you choose an AR3, yeah? So that's how you use it. Really simple tool, really simple tool. So we've now got these two tools that tell us how to model the dependence in a time series, really simply. You use the ACF to determine whether the series is stationary. If that thing dies down and stays inside, cool. So if it's died down by the time you get to 20, you're good to go. Okay? So the first one, the ACF, is used to determine stationarity. The second one, the PACF, is used to determine what order model should you fit. And the rule there is pick the last one out, the last spike that's outside the dotted lines, and use that. Okay? So for this particular data, we can say two things. ACF damps down to within the dotted lines. Seems annoying. There we go. Within the dotted lines. So the dotted lines have names. They're called the asymptotic bounds, in case you care. Okay? Because people say, well, you're calling it dotted lines, that's not very technical. Am I going to impress people by saying dotted lines? Oh, okay. You can call them asymptotic bounds if you want. This means that the series is stationary. Okay? Second comment. The PACF has its last significant spike at lag 1. Lag 1. Right? The last spike that was outside was at lag 1. This means fit an AR1. So what we've done is we've identified what model we wanted to fit now. So that's why it's called ident. We're identifying the model fit. And it's got a name, you can see at the top, Box-Jenkins, right? So Box is a guy named George Box. He's the guy who said, we've quoted him before, he's the guy who said all models are wrong but some models are useful, right? That's George Box. I don't know who Jenkins was. Tagging along. Box is by far the more famous of the two. Okay? So they come up with this method for determining what model to fit in an autoregressive framework. So it's really good. It works really nicely. Now we have to talk about a couple of things. The first thing is what happens if the ACF does not die down, if your series is not stationary. Okay? If your series is not stationary, then you need to try something else. Okay? There are two options. One is to do nothing and hope it goes away after you fit it. That sometimes works. Okay? Second option, try a technique like differencing. Sometimes if the original series is not stationary, the differenced series is. Okay? So, if the series is not stationary from step one, either fit the model anyway and see if the problem goes away. Okay, that technique does sometimes work, more often than you would think. Or try differencing the data and doing over, right? Modelling again. So if the series isn't stationary, you either give it a go, see what happens, right? Fit the AR1, see what happens, or try differencing the data and remodelling. Okay? All right, now how do you fit these models? Okay, here's the good news. There is a command in the class data, a function in the class data, which fits all the models between an AR1 and an AR10. Okay? So there is a function called capital R AIC, which fits everything from an AR1 up to an AR10, and then you just pick out, the one you want. Okay? So it's called capital R AIC. So our series at the moment is fits dollars resid, right? That's our series. So if I go something, give it a name, AR fits equals capital RAIC of fits dollars resid. So what that's doing is it's taking my errors, right, like from my trend seasonal model, and it's fitting an AR1, an AR2, an AR3, an AR4, right up to AR10. Okay? You'll notice when I did that, it's actually doing a lot of work, right? Because you watch the screen carefully. You know, normally you do stuff in R and you get an answer straight away. Watch. 1,000, 2, 1,000, 3, 1,000, it took 3 seconds, right? You know, and these computers are fast, so that's takes a while, okay? All right, what does AR fits look like? If I look at AR fits dollars coef, these are the coefficients, okay? I'm just going to make the screen a little bit bigger so we can see. I'm just going to pump this to the screen. Oh, before I do that, options digits equals 2 so that we don't get 17 digits in each number. That's just nuts. And let's look at AR fits dollars coef. Okay, there they all are. So, it's a matrix. The first column are the parameter estimates for an AR1. So how many parameters do you need for an AR1? 1, right? A1, right? So A1 is 0.61, just leaves all the rest as zeros. Okay? So an AR1 would be xt is 0.61 times xt minus 1. Then the error term's gone, right? So we fit it. All right, an AR2 would look like xt is 0.581 xt minus 1 plus 0.093 times xt minus 2. And the rest are gone, right? If I wanted to fit an AR10, I'd probably have to go take a little lie down, but there it is. xt is 0.58 times xt minus 1 plus 0.15 times xt minus 2 minus 0.16 times xt minus 3 minus 0.066 times xt minus 10. That's what an AR10 would look like. Okay? So all we do now is we just pick out the one we want. Which one do we want? The first one, right? So we just pick out this one. So our model for dependence is xt, better put bracket, hash, xt equals 0.61 times xt minus 1. That's my model for dependence. Okay? Now, that's the coefficients. The other thing you'll use out of the the RAIC rake output are the residuals. That's what's left over after you've done all the modelling. So we did trend, we did seasonal, then we modelled the dependence. Okay? The residuals is what's left over. So, AR fits dollars resid is also a matrix. It's got 10 columns, right? The first column is the residuals from an AR1. The second column is the residuals from an AR2. The third column is the residuals from an AR3. People are falling asleep. It's boring, right? Fourth column, AR4. Fifth column, AR5, and so on. So you get 10 columns, each a set of residuals for a different model. What do we need? Just the first one, right? So AR dollars resid first column, these are residuals from an AR1. Okay? Residuals from an AR1 are the first column. So I'm just going to call those res. Res equals AR fits dollars resid, comma, 1. Now, just to check if you've been listening, what would the residual from an AR6 be? Which column? There are two numbers that start with 6 and 7, right? Which one is it? 6. 6, right? Sixth column would give you the residuals from an AR6. Huh? Okay. I know it's boring. But you know what? Wouldn't it be worse if it wasn't completely bloody obvious? Right? Because then I'd be getting emails going, why do you use the 14th column? You don't. You use the 6th column if you want an AR6, right? So really simple. Okay, so these are my residuals at the end. All right, now, these should have nothing left. If I do an ident on these residuals, these should be white noise. So this is what white noise looks like. The ACF should have a spike at lag 0 because everything's correlated with itself, but then nothing else. Okay? And the PACF should be nothing, 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 and it's more nothing after that. Okay? Because it's white noise. You got it all, right? You're done. You're done. So we're done. That's our model. All right, so what's our overall model? Okay, you look at fits dollars coef. Okay, that's the first bit. And then you look at AR fits dollars coef first column, right? And now you can write down your entire model, and you have to do that. So let's write down our entire model. Alcohol at time t equals, all right, here we go. 1573, I'm going to leave off what's after the decimal point, minus 1.7 times time minus 1982. Remember we centred time. Minus 1.23 times time minus 1982 squared, right? Plus 0.18. Where's the seasonal stuff? Oh, look, what did I do? I didn't put in fits. I meant fits. That S stood for seasonal. There we go. All right, I'm going to write it down now. I'm just going to say it. If you don't know what it is now, there probably ain't no hope for you, right? Because how many times have we done it? Okay, I'm going to say it. Alcohol at time t equals 1576 times, that's the intercept, minus 2.82 times time minus 1982, right? Minus 1.45 times time minus 1982 squared, plus 0.24 times time minus 1982 cubed. That's the cubic trend, okay? Minus 68 times an indicator that you're in winter. So that only gets picked up if you're in winter. Minus 46.78 times an indicator that you're in spring. That only gets picked up in spring. Plus 183.49 times you're an indicator you're in summer. Okay? That's the first part of your model. Plus xt, where xt is your irregular. Okay? So you write all that down. Okay? So alcohol, because I have to write something, don't I? Alcohol at time, alcohol T equals, so I'm just going to go 1576 plus plus 183 times an indicator that you're in summer, right? So that was what the model looked like. Then we go plus xt, okay? That's your first line. Your second line is xt equals 0.61 times xt minus 1. All right? Now, what do we got here? We write the model in two lines because the first line is the structure and the second line is the dependence. Okay? Structure, then dependence. You predict xt to be 0. You predict it to be 0. Okay? It's an error process. So it's predicted to be 0. If I ask you, what is the alcohol going to be in winter 1997, you'd put in time equals 1997.5, which is winter 1997. You'd plug it into the top part here. Okay? You wouldn't pick up a summer term, you'd pick up the winter term, which is minus 68. This you'd predict to be 0. Okay? And your dependence would be summarised here. This does not play a role in prediction. Dependence plays no role in prediction. It is only to understand how related one point is to the next. It gives you an idea of the correlation between now and tomorrow, or now and, in this case, next quarter. Okay? So that's how you model the time series. Now, the very last thing you do is you've got now a noise process, which is this residuals, okay? And then you produce all of the usual residual plots that you do when you've got residuals from a model fit. Okay, so let's have a look at that. Whoops. It's waiting for me to do something here. Stop. There we go. So these are all your normal residual plots. What's it doing? Stop, finish. Sorry, there we go. Okay, so what do we got? We've got, this is the residuals plotted against time. We normally do this in a time series just to check that there's no wiggles left. Okay, this is residuals versus lagged residuals. This is a QQ plot of the residuals, and this is the absolute residual plot, okay, against time. And so you can use these to make the usual judgments around, okay, is it homoscedastic, is it normal, all those kinds of things. So these are just your normal residual plots that you would always produce after any model fit. Nothing new here. Nothing new here. Okay? And then you're done. So, that's the basic structure. Now, what we need to do is we need to think about how we're going to handle any time series, because we've looked at the alcohol data, right? Well, the good news is, I think you'll find this to be really good news, right? You've got an assignment coming up, you've got a data set, you want to know what to do. How am I going to handle this? Okay, let me tell you. So, we'll call this time series modelling (101). Time series modelling 101. Okay? It's only 101 because this is only the most simple time series, right? We're only fitting really simple models here. So 1. These are the steps you've got to take. You don't take these steps, not good. Okay, first step, plot the series. Okay, plot the series. Plot the series, look at the plot. Okay? Now, this is how every analysis starts, right? If you don't start every analysis by making a simple plot, you are so screwed. Particularly in a course where plotting is the thing, right? But in general, right, if you don't look at the data, you deserve what you get, which is a bad analysis. Okay? So plot the series. What are you looking for? Well, you're looking to know, is it homoscedastic or not? In other words, is the variance constant? You're asking yourself, what is the trend going to be? Where's it going? You're asking yourself, does it have a seasonal component? Okay? These are your initial questions. Is it homoscedastic? Simple test. Take your 2 fingers, top and bottom of the data, run them along. If your 2 fingers stay the same distance apart pretty much as you move across, you're good. If they move further apart, you're probably heteroscedastic. Okay? If the answer to this is yes, then happy. If the answer to this is no, then you're probably going to want to transform your data. Okay? Transform. Now, you notice I didn't put a sad face. There's nothing sad about transforming, particularly. It's not as happy. Maybe we'll just make it not happy, not unhappy. It's just what it is, right? Yeah, it's cool. We can do it. Okay, so what's your trend? Okay, think. Is there no trend? Is there a linear trend? Try and think of what polynomial to fit. Is there a quadratic trend? Try and make a basic decision. Is it a cubic trend? Okay? If you get down to a 9th order polynomial, slap yourself. Right? Don't fit high order polynomials. Just ask yourself, linear, quadratic, cubic, maybe quartic. You go beyond that, you're probably being silly. Okay? Seasonal. You ask yourself one question. Is it regular? For it to be seasonal, it has to be regular. Okay? That means if it's quarterly data, every 4 times. Boom, 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 boom. Right? And then again. Boom, 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 boom. And then again. Boom, boom, boom. That's the nature of regular. Boom. Okay? Regular means every 4th time. Oh my God, it's summer again. Yeah? You know how that works. So all of that stuff is done by looking at your initial plot. Is it homoscedastic? What do you think the trend is? Is there a seasonal component? Right? Okay. Second step. You pick them off one by one. Fit the trend. You decided what to do in the first step. You think, maybe it looks cubic. I'm going to fit a cubic. Remember, if you're going to fit a higher order polynomial like a cubic or a quartic, you're going to need to centre time. Okay? Which will generally mean just taking time minus some value near the middle of the time scale. So I chose 1982, could have chosen another year, wouldn't have mattered. So fit the trend. Okay? That's generally going to be a polynomial, or you could use differencing. It's up to you. Okay? Second step, fit. We're going to restrict ourselves to constant seasonal models. So fit a constant seasonal. Okay, that's going to be the next step. Okay? So we fit this, we get residuals from this fit. Get residuals, then identify model. Identify model. Use the ACF to check whether things are stationary. use the PACF to choose P from an ARP. So decide how big your model's going to be. Okay? Use rake to fit the model. Okay? Easy peasy. Once you've got the residuals, identify the model. ACF to check if it's stationary. PACF to choose the order. Use rake to fit it. We're nearly done. 2 more steps left. Check the final residuals. So those are the usual residual plots. Last step, final step, write down the model. In 2 lines. Right? ZT equals structure plus XT. XT is going to typically be an ARP, where P was chosen earlier. Okay? Yes? Yeah. Yes, ACF first, because if the series isn't stationary, you're going to want to do something. Okay? Then PACF. If the ACF doesn't damp down, then you've got 2 options. Proceed and see if the problem goes away. Okay? By goes away, I mean the residuals that you get don't have that problem. Okay? Sometimes it goes away. Or difference. Yep.
Sometimes the QQ branches show how it out.
Yep.
So.
Okay, so yeah, look. When you model, you ask for an awful lot to work out, right? You ask for the structure to be right, and then you ask for the residuals to have no dependence after you've modelled. And then right at the end, you go, I want my residuals to be normal, 0 mean, constant variance. Well, it's like I told you before. You're trying to choose a life partner and you want them to be wealthy, good-looking and good in bed. You're not going to get all 3, probably, right, unless you marry me. And my wife says. And, well, maybe not so good-looking. Not really wealthy either. Maybe she got none, I don't know. Anyway, so, yeah. So if at the end your model's great except the errors are slightly non-normal, yeah. Remember, even if your model looks great, guess what? It's still wrong, because all models are wrong. Right? So, yeah. Now, here's my words of the wise, words for the wise for you. Let's make this small again. So it all fits on one page, right, as near as I can get it. Okay, these are your steps. When you're doing the assignment, this is your script, right? Follow these steps and you'll be fine. Assignment 2 is not hard, okay? It's not hard. Now, that's not to say it's easy either. You'll look at the data and you'll go, that looks different to what we looked at before. Yeah, of course. Every data set's different, right? And there are going to be things you'll have to scratch your head about and think about. That's okay, right? Thinking is allowed. In fact, it's probably recommended, right? But you follow these steps and you won't go wrong, okay? So, what do I need to see in your assignment? I need to see a plot of the data, okay? I need to see you checking. Is it homoscedastic? What's the trend? What's the seasonal? Thinking about what each of those things are. You might get different answers to other people. That's cool. These are all judgments. Remember, all models are wrong. All models are wrong. Some models are useful. Some models are better than others, right? Then you fit the trend, fit the seasonal. Get your residuals. Use ident, capital IDENT. Look at the ACF, the PACF to decide what model to fit. Use rake to fit it. Check your final residuals and write down the model, okay? Write down the model. Every single one of these steps needs to be done, right? If you get to the bottom and you don't write down the model, that's not good, That's not good, because that'd be like me going to see a movie and then leaving 10 minutes before the end. I know what happens, right? That's no good. Or reading a book and stopping, before I read the last chapter. Yeah? So, make sure you write me down the model. Use 2 lines. All right? Okay, so we have a few minutes left. Let's have a look at a different data set. You have another question? Go for it.
Yeah. You could be the comment to choose the P from 1 to AR10, but if the model has more amount.
That's a good question. So what happens if your PACF says fit an AR15, right? Yeah, what do? Don't fit an AR15. I'll tell you why. Okay, I'll tell you why. So, we've covered time series in what, 3 days? And time series is a pretty deep subject, right? So we didn't do it in 3 days because I'm the best teacher ever. That's not true, right? We did it in 3 days because we fit very narrow selection of possible models, okay? So if you've done courses in time series, you know that as well as AR models, autoregressive, X depending on its past, there are models called moving average models, MA models, and there are more complex things, AMA, autoregressive moving average models, and there's more, right? An MA model is a very simple model. I mean, I'll tell you what it looks like. It looks like xt is equal to error plus error t minus 1 plus error t minus 2, and so on. All the dependencies on the error side, okay? An MA1 looks like an AR infinity. So long-range AR models probably aren't really AR models that you're trying to fit. You're probably trying to fit an MA model, okay? Now, we haven't gone there in this class. You do not have to fit ARIMA or MA models at all. So, if you see a spike out at lag 15 and that's the last one, ignore it, is my best advice. It can happen, by the way, but generally speaking, the spike will be only just outside the dotted line, right? And there you have to apply the common sense test. These dotted lines, they're kind of big sample bounds, right? So if you've got a small sample, you might go outside just, and it's not really that important. So, yeah, that's a very good question. All right, so kiwi fruit data. Let's have a look at that. Have I got the kiwi fruits here? I do. So let's have a quick look at the kiwi fruit data. We're not going to have time to do much. Let's do the first basic things. Except let's do it in a size that everybody can see. Let's do it again. Okay. So there's my kiwi fruit data. Oh, you can't see what I can see. Fair, good call. You know, I once went through 15 minutes of a lecture before someone told me. I'm like, okay. Obviously, they just love the sound of the voice. That's it. There is that TV series, The Voice, where they pretend they don't look at anybody and they choose the pretty people. All right, so these are monthly kiwi fruit exports from New Zealand. All right, let's go through our process, right? You've written the steps down. Let's go through our process. Plot the series. Done. Is it homoscedastic? Get your fingers, you move along. Uh-oh, they're getting wider apart. It's not homoscedastic. Going to have to transform this one. All right, well, before we move any further, let's do that. Let's take logs. How's that one? Yeah? Pretty good? Pretty good. Okay, so that's my new series. Let's ask ourselves the next question. Is there a trend in this? Is it flat? Flat? Do this if you think no. Do this if you think yes. No, it's not flat. It seems to be going up and probably linearly, right? That's cool. Quadratic? Who's for quadratic? Seems like a stretch. Cubic? No. So probably linear. Okay, so there's decision one, probably linear. Okay. Is there a seasonal effect? Is this repeating? And is it regular? Seems so. Yep. And so you can actually count the number of points between the bottoms, or the tops if you want, right? Turns out there's 12. Okay? Makes sense, right? This is years. Kiwi fruits grow. They obviously like to grow in one season and not in the other one, etc. So this has a cycle. This is the frequency of the series.